at Markforged, I support some of our aerospace and U.S. federal customers, working with them on applications and ensuring they're getting most out of their 3D printing systems. Markforged is a leader in additive in both the composite and the metal world. We've got industrial printers that are easy to use and really make additive accessible to a lot of people. So on the composite side, the Hawkridge team is going to talk both about our composite and metal systems. They are one of our, I think, our largest partner and reseller, and work hand in hand with Markforged and our customers to help deliver solutions to our customers.
Is this working? Yes. Hello. I'm going to get this to Andrew, but I'm Paul Keefe with Hawkridge. I cover all of New England from Maine down through Connecticut. Just going to mention before Andrew takes it over, I think it is what Jeff was talking about earlier, all about access, getting the equipment here, getting everybody to utilize that. We're kicking off our brand new showroom that Hawkridge has in Massachusetts. Come see me after, give you more information about that. It has all of our technologies, really cool stuff up in Boston. Access to the printers at Markforged in their new headquarters in Waltham, the old Polaroid building. I just went there last week. Phenomenal place. We'd love to have you there as well. But I'm going to get this over to Andrew Garchik for him to get going on the Metal X and take it away. Andrew.
All right. Thanks, Melissa, Jeff, Paul, for the warm welcome. My name's Andrew. I'm an application engineer with Hawkridge Systems. Been in the industry about 6 years, and I'm speaking to you today because I've had the opportunity to work with the Metal X in my lab about the last 5 years. And what I have for you today, we're going to start off talking about the Metal X and the process so you guys understand the equipment and exactly how it works. Then we'll go into some applications because it's great to print metal, but if you don't have a reason to use it, then it's what's it for, right? So we'll talk about where other companies are finding opportunities to print with metal. Lastly, a quick slide on what's next. Markforged has a new printer coming out. They just launched at Rapid 2 weeks ago, so I'll quickly hit on that as well. And then lastly, we'll do some questions and move into the tour where we have the Metal X in the other room. So please come over to our table and come look at the parts and the machine. And I'd be happy to show you guys under the hood, so to speak. Okay, so before we dive into metal, I just want to point out that there are 2 other Markforged machines in-house here. There's the Mark II and the X7. And this is what Markforged was originally known for. This is how they went from a garage to a publicly traded company. And it's the ability to put a continuous strand of fiber into plastic to make a true composite. And I'm not going to get too much into it, but it's really cool. And we also have parts to show that off as well. So if you don't know about it, check it out. Really cool stuff. We're here today to talk about the Metal X, or the digital forge. Called a digital forge because you start off with a file and you wind up with a metal part in the end. It's 3 pieces of equipment. There's an FFF 3D printer, a wash station, and then a sinter furnace. And then at the end, you've got a true metal part. So some of the things to know, kind of high level. 1, there's no loose metal powders. So systems that have loose powder, you know, it's toxic. You can't breathe the stuff. It absorbs through your skin. So when you're operating systems like that, you have to have on some PPE, a respirator, at least gloves. Some folks will, you know, make you put on kind of a onesie so you don't get a little powder on your sleeve, that kind of thing. So very safe system, no loose powder. It's actually bound in plastic and wax, so it's safe to handle. 2, it's cost effective. This is a low barrier for entry. The systems that I've seen out there can cost 5 times as much, you know, $1 million systems, and easily twice as much. So this is a less expensive way potentially to get into metal printing for some companies. And lastly, it's easy to use. I know I'm standing up here in front of you guys today and you're going, oh, he must know something if he's up here. But literally, if I can do it, you guys can do it. I never touched a gas tank in my life before working with this system. And I got a little bit of a sore throat, so I might be drinking water quite a bit. Oh, really lastly, I just wanted to point out that CCAT does have a fourth optional piece of equipment here called a BOFA unit. It's a fume extractor. The wash station and the Sinter furnace both have exhaust. And in my lab in New Jersey, that gets vented out. I'm sure you can do the same thing in Connecticut. But for facilities where you might not be able to create a pathway to vent the gas out, or if you have an EHS department that's a little aggressive, then you can use this BOFA system and it filters out the exhaust and, cleans it with filters. All right, so the process, atomic diffusion additive manufacturing, or ATOM. It sounds like there's a nuclear reactor under the hood, right? But to be honest, it's very simple. It's simply a combination of FFF printing and metal injection molding post-processing steps. You design your part, you print it in the green state, you wash it in a solvent, you sinter it, and in the end, you have your metal part. The process is a lot like metal injection molding, except injection molding is really good for high volume, and this is the same thing but geared for low volume. I'm showing here this retired Lego mold. It's the mold that makes those little rectangle pieces, one of the most popular pieces. And you can see it's pretty, sophisticated. There's a lot to it. What would you guys guess if you want to throw a number out there? How much do you think that mold right there costs? That's a good guess. Typically molds, I'm not an injection molding expert, but typically molds from what I see are somewhere between 10 grand and 100 grand, and that looks like an expensive one. But no, 250,000 says the internet. So for high volume, that's great. You're trying to make millions and millions of parts, then injection molding is the way to go. But if you're looking to do onesie twosies or change your geometry often, then you can start the process with an FFF 3D printer instead of using a mold. So injection molding is mold wash sinter, and we do print wash sinter, but very, very similar processes. So the filament is on a spool. It's an FFF 3D printer and super easy to use. You don't have to level the bed. You don't have to do the nozzle heights. Everything's automatic. But what these guys figured out is that if you take the same ingredients in the same proportions in metal injection molding and form it into a filament, you can just print the stuff instead of molding it. So 3 ingredients, metal powder, wax, and polymer. You might be saying, Andrew, I thought you said no metal powder. There is metal powder, but it's bound in wax and polymer, so you can handle it and you don't have those similar safety concerns. We've got some tool steels, A2, D2, and H13, cold work and hot work, 17-4 stainless, pure copper, can be used for heat sinks, induction coils, bus bars. It is pure copper. A lot of folks print copper alloys, but we use pure copper because it has the highest thermal and electrical conductivity. And Inconel 625, which Melissa could tell you is widely used in aerospace because of its chemical resistivity and ability to resist thermal cyclic loading. All right, so let's get into the process a little bit. So you start off with a green part that you print in the printer. And you can see our operator there, no PPE, your hands are right in the machine. And you've got these 3 ingredients. There is kind of a side note here. There's a 4th ingredient, which is the ceramic release. So there's also this material that's ceramic powder bound in plastic, and that goes in between the part and the supports because it is FFF printing. So you print your supports in metal, and it allows the part to release from the raft later on, which I actually have a little video, so I'll show you guys what it looks like. Second step, the parts go into a wash station, which is a simple solvent bath. There's no real heat. There's no ultrasonic. It's just a bath in Opteon SF79, which is a common fluid used by many injection molders around the country. So now you've gone from 3 ingredients, metal wax polymer, down to only 2 ingredients, the metal powder and the polymer. Third step goes into the sinter furnace, and the metal particles will now fuse together and fill in all the space that was left from the wax and the polymer. And you see about 17 to 20% shrinkage. Good news is that shrinkage factor is pretty figured out. They've been doing injection molding for, God, must be 40, 50 years. So you simply put your part in and the software figures the rest out. It'll print the part larger so that it shrinks down in the end. And just a little bit about what actually goes on in the sinter furnace. So this is temperature versus time. The heat will increase up to a point where the polymer could get vaporized out. And then once the polymer is out, it raises the temperature again to the point where the metal particles will actually fuse together. And that's, I guess, where the atomic diffusion out of the fancy name comes from. And then it cools, and then you have your part. So post-processing, parts are on a raft. A lot of the time, you don't have to, but it gives more uniform shrinkage in the sinter furnace, and certain geometries you can get away without the raft, but most times you'll be printing with the raft. So I did the hammer method on the video, like the drop it on the floor method too. It's kind of fun. So right off. The white powder you're seeing there, that's the ceramic and polymer. Now there's no more polymers in the ceramic turning to powder. And you can see it's kind of a unique structure on the bottom of this part. The supports come off. All right, so let's look at some applications, right? Where can you actually use this stuff? Where are folks using it in the industry? There's 4 major buckets to look at. First one is tools and fixtures. This is probably the biggest one. I've got a picture here of a welding fixture, and you can see it's got really cool knurling features on it. It's got part numbers. That's one of the advantages of 3D printing. You can make complex surface features. You could put instructions on parts. You could put thread sizes, you name it, whatever you want onto your part. And lots of fixtures. That's a very common application. Resting fixtures, assembly fixtures, CMM inspection fixtures, you name it, all these different fixtures. And I threw a custom tool up there too, a tamper-proof wrench. That's a hybrid part that uses the composite technology as well as the metal as a tip there. And that's kind of nice. Like Jeff said earlier, it's just another tool in your toolbox. And when you use all your tools, that's when you get the best part. Second, MRO, maintenance, repair, operations. So let's say that you've got some old machine in your facility and a part breaks. So now you have a way to produce that part. Maybe the company's no longer in business or they don't support that machine anymore. But other stuff I've seen at MRO is upgrading old equipment. Sometimes folks will try to bring their equipment up to the level of the newer equipment by adding new safety features, new sensors, stuff like that. So very common to make bracketry, cable management, all kinds of stuff like that. So MRO winds up being a big one. End use parts. This is an engine mount. So it's just a 1-for-1 replacement of something that broke. And I've got a couple end use parts coming up in these specific examples in the next few slides. So get into it then. And prototyping. I know everyone's bored of prototyping and 3D printing, right? Of course, that's a big use for it. You'd think once you get into metal, like, oh no, we're printing metal now, so we're not going to be prototyping. But no, you see it a lot out there in the field. And this example here, they started off first in composite, then they prototyped it in metal, and then they got to their final part. And the systems are accurate enough that it can actually, be a good pathway from one to the other and be successful. So those are the 4 major buckets, but now I'm going to go into some specific examples here. So the first one is from Stanley, Black&Decker. It's an actuator housing for a trigger for a pull driver. So one of those pull drivers that knock the posts into the ground. And the original part is on the left, the 3D printed one is on the right. And basically the way it works is there's ball bearings that run through this, and as the ball bearings move, it actuates the trigger. So first thing I'd like to point out is that they've done some design change for this part. They took advantage of the process and designed for the process. You can make parts one-to-one, but if you're designing for the process, you're going to get a big added benefit. So we always recommend that. And if you look, you can see the circular channels now have teardropped or angled roofs on them. You don't need a round hole to roll a ball bearing through it. And that allows for the part to print without supports in the cavities, so it makes it a little easier on the printing side. Another thing here is a curved cavity. So this cavity goes from one side, curves around to the other. And as you know, you can't drill a curved hole. So it's a nice added feature you can do with additive manufacturing. But the real point I want to make with this, and this is a point that sometimes it's still, people don't realize this, looking at cost and looking at lead time is really great when you're trying to get ROI in a part. But look at what happened here. The original part had a housing that was cast and machined, then a plate that's laser cut, and then 2 bolts to put them together. So you have to have all that expertise and equipment in-house. I mean, think about how many people had to touch this part, right? It had to be cast, machined, laser cut, and then somebody had to assemble them. And I don't think that this is a high volume application. I think because they use the Metal X. So probably they're making more like hundreds of these or thousands or something like that. So somebody has to put all those together, where with 3D printing, it's set it and forget it. The engineering team goes, they hit a button, they come back. Yeah, you have to move the parts through the process, but there's no real labor. You don't have to watch it. And, think about that. The machinists, the tool and die guys, they never even knew it happened. This part was produced by their engineering department, and it takes the load off of the machine shop, which is really great for 2 reasons. One, I talk to manufacturers all the time. It's very common. They say it's an epidemic that they're having really hard time finding skilled labor. So these machinists are retiring faster than they're coming into the field. So if you can lighten the load on the machine shop and switch it to the engineering department, that's a huge added benefit that a lot of folks are seeing. And second, and you'll see this in the next example, is let's say, we're great. Our machine shop's great. We're a job shop. It creates room for more work. If you transfer all your tools and fixtures to the engineering department, now your job shop's available, or your tool room's available to take on more work, which is exactly what these guys did at Lean Machine. So Lean Machine makes robotic gripper jaws or fingers for the end of their robotic arm. They have an automated bending cell, and all it does all day is it takes these little blanks of sheet metal out from an area where they're kept, and it puts it into actually a 3D printed punch and die set, which is really why I love this example. You got 3D printed fingers putting the blanks into a punch and die that's 3D printed with a composite system, and it bends the piece of metal, and then the fingers grab it again and put it in a pile. And that's what it does all day. And there's a great video on this online. If you go on YouTube, look up Lean Machine Markforged, a great 3-minute video with the engineers talking about all the benefits. But one thing I would say is they love their jaws that they made, the punch and die, because it is made out of composites, so it doesn't mar their parts, which was a problem that they had previously. But for the fingers, they saw, I'm not going to read these numbers. It's your typical use case. It's like blow your mind numbers. Drastic reduction in lead time and cost, and a big reduction in weight, which is really great for end of arm tools. You could run them potentially faster and maintain the same accuracy, if you lightweight the tools. And again, it eliminated reliance on their shop for tooling. So now they can say yes to more work, and they do. And they utilize the hybrid part. So you can see, again, this part's made from a composite body and a little 3D printed metal tip. I have all these parts for you guys to see, by the way. And they put it together with 2 dowel pins. And when they switch to a hybrid part, again, using all the tools in their toolbox, now they're using aftermarket hardware, composite printing, metal printing, or this could be a machine metal part too. They're getting the most out of it. And if you look, probably hard to read from over there. If you look at these metrics, their cost was cut in half again, and they cut their weight by more than half. So by using a hybrid part, they really were able to take advantage of all the tools at their disposal. Okay, Goering. This is a really interesting one. So Goering is a world-class tool maker. They make cutter bodies for mills. And it's one that I like especially because you'll see in the next couple slides that I actually recreated this. This is I stole their idea. This is my version. But I wanted to go online and do a little research. I said, I might get some questions like, are they really selling these or did they just make one day? Or like, what's the real story here? So I found an interview online where they were being interviewed about their cutting tools, specifically 3D printed cutting tools. And it's cooler than I even thought. Like it's hard to even say this without sounding salesy, but the gentleman said that the 3D printed versions, the tools actually last longer and they see less noise and less chatter. And they asked the gentleman why, and he was like, I don't know, but I think because it's the infill. So you can print these parts less dense than solid metal, thereby reducing the weight. And he felt that the infill also helps absorb some of the vibration and energy to get less noise and less chatter. Lastly, this part has a feature that you cannot do with traditional manufacturing, which has been mentioned here a few times today already. It's got conformal coolant channels. So again, you can't drill a curved cavity. So coolant usually on a mill will run externally through tubes on the outside, and it cools the tip and it brushes away the chips. And the way that it brushes away the chips affects how good the tool works. So with conformal coolant channels, they run these channels and they get the exact cooling that they want in the tool, and it shoots out at exactly the right angle so they get the best possible chip flow. So I thought that was really neat. So I went in, forgot. Also, the time to produce the part was heavily reduced from 4 weeks down to 1 week. So think about that. You're a tool maker, you're world-class, you're kicking butt, right? You have a great company. And then a technology comes along where you can make your parts 75% faster. That's like mind-blowing change. So, yep, I stole the idea. I made my own. Doesn't look quite like theirs, but we picked, kind of a very common cutter body geometry, and we redesigned it. We put in our own conformal coolant channels. I decided to get a little crazy with it, made really snaking around S turns. The idea was to take the coolant or take the heat out of the bottom of the tip that's on there, a carbide tip, and then it snakes around and again gives you the opportunity to point it any direction that you want for optimized chip flow. And for Goering, they actually braze their tips on. I don't have brazing capability at my lab, so we simply designed the holes to be a little undersized. We reamed them so they were perfect, tapped them, and we bolted on our tips instead of reaming them on. So this is the end of this section for the Metal X as the grand finale. It might be anticlimactic, but threw a little video up here of Cool. So last thing I want to mention here is the new printer coming out from Markforged. They just launched it 2 weeks ago at Rapid. I was lucky enough to be there, and it's very new, so I probably can't answer the toughest questions on this, but I wanted to tell you a little bit about it. So Markforged bought a company called Digital Metal last year. They had a finished binder jetting solution that was highly successful. And, I'm sure it's a little more complicated than this, but just generally speaking, it basically does powdered metal, then comes back with 70,000 inkjet nozzles like a 2D printer, hits it with glue just in the spots that the part's going to be. And then it does powdered metal glue, something like that. You pull it out of the powder, you put it in the sinter furnace, you sinter it, and then you get highly accurate, very precise, tiny parts. And I threw one example up here. This is just off their website. They printed their entire company 10 millimeters tall. And when you zoom in on this, the detail is incredible. Like you can see the wrinkles in his shirt. You can see the space under his collar, you know, and it's like this big. So really impressive. I do have one part from them at the table. So if you guys come by, just ask to see it. I don't have it out because it's tiny. So I don't want it to disappear. And that's about it. Thank you guys so much. That's the end. And I'm happy to take any questions if you guys might have.
Thank you very much, Andrew. Questions?
Might as well let the online guys hear.
Sorry, so with the amount of shrinkage on that first machine, the X machine that you're showing, ultimately, what kind of tolerance can you hold on your finished part?
Gotcha. So the common question, the parts are near net shape. So it's kind of similar to what everybody's been talking about. You know, just to give you a quick example, I printed a part that's really good for the geometry, a little cube with curved edges on it. And I said, let me feed it whatever food it wants to eat and see what happens. It was off by 2 thou in the X, by +2 in the X, +2 in the Y, and about +6 in the Z, which is common for FFF 3D printing. You'll look higher accuracy in the XY versus the Z, but it's kind of a tough question to answer because it's highly geometry dependent. Likes parts that are about the size of a softball or smaller. Typically, I tell folks, it likes thin walls, less than bulkier parts, although I've seen what CCAT's been printing the last few days. These heat sinks with extremely thin walls and thin features. So maybe rolling back on that a little bit. But it's geometry dependent, and big parts will be a little looser, smaller parts will be a little tighter. I think the best way to look at it is to, if you're really looking into this stuff, to do a test part, print your part. We can print it out for you. CCAT potentially can print it out for you guys and measure your part. So I hope that helps. Hard question.
Right. So with the Metal X in particular, who's buying those?
So it's very varied because just about anybody with a tool room could use one of these. So we see every kind of company from a small job shop all the way to like mega aerospace companies that Melissa works with. So very varied, but yeah, actually because of the kind of better safety features, we see these in a lot of universities where they don't want powdered metal and stuff like that. So in EDU as well.
On the washing station, what kind of lifespan do you have on the fluids? Do you have to change it out? How much, per amount of printing volume?
Sure. Yeah, it's fairly easy to keep the wash station running. You're going to want to top it off every 2 weeks with about a half gallon of fluid. So pretty easy. You just got a 5-gallon drum, put on top. You have a little siphon, has a little fill line. You just fill it to the fill line again. So probably costs you somewhere about $100 to $125 a month to keep that wash station rolling. And about once a year, you do have to drain the boil chamber, which has the trapped wax in it. And that's pretty easy. You just put the jug behind the machine. There's a little spigot. You empty it out and away you go. You put in more fluid and you're good to go. You do have to have a waste disposal company dispose of the leftovers. But it's not very expensive. I'd say somewhere in the neighborhoods of about $200 a year, something like that. Sorry. Oh, the cost of the system. Yeah, I tried to let Paul and Melissa answer those questions. It's like the one thing I'm allowed to stay out of. But let's just say ballpark. Should I throw a ballpark? Is that okay with you guys? Let's up like 200K. So, yeah. So it's fairly inexpensive. I mean, I can't afford one in my garage at home, so I can't say it's, but comparatively, relatively to other systems, it's fairly good.
All right. Thank you very much, sir.
Thanks, guys.
Appreciate it.
Really appreciate your time.
So on the agenda, we have a few minutes that we had earmarked for technical questions. And before Andrew walks away and Chase is here, I'm not sure where Robert went. But I just wanted to give everybody an opportunity, once again, if you had any technical questions specifically regarding the Metal X system or any of the composite systems as well, or any questions for Chase, we would take a few minutes and try to handle any more technical questions before we move on to the last sections of the meeting. All right, this online.
So this question is for Markforged. Is there any in situ measuring and feedback capability to dial and shrinkage compensation?
So, yes and no. So Markforged we have ITAR compliant software, but we also have cloud-based software. While our customers are printing, we're collecting metadata, not detailed part data, but understanding of how parts are printing and if they're printing well, not printing well. There's feedback on the printer. You can give it 1 to 5 stars, like how good was that print. Also, we have, I want to say, 100+ printers in-house that we're constantly improving our printing capabilities and understanding that shrinkage and compensation for it. So it's constantly getting better. We throw out software updates basically almost like once a week, once every 2 weeks, where we're continually dialing that in.
Just to add to that, it's pretty common with Markforged for them to be adding new features and stuff as you go along. They're always working on their software, working on their printers. They're kind of over-engineered so they can update them with firmware updates over the air. And my little example I wanted to throw in was I actually own a Mark I, the original like prototype Markforged printer. And they had some big updates recently, and even I got them. And it's like a 9-year-old printer that's not even supported anymore. So you expect updates.
Hey, sorry. It's kinda loud. I have a question for Chase. I'm actually a UConn student. I'm studying material science, so I had some more kind of questions about the metallography side of it. So you showed kind of like equiaxed grains in your piece, but when you look at the pictures, you can kind of see like features. So is it actually equiaxed all the way through, or is there some variation depending on where you are in terms of like the spinning?
You're mentioning like the the appearance of the material as printed on the outside.
Yeah, exactly.
Yeah, so we refer to that as flash. So it's expelled material outside of the deposition zone. No, so the grain size is pretty constant throughout even those flash zones, but you do see the flash that flowing out material. The process is pretty symmetric, but there is some just differences across that zone as far as temperatures go. So you may see, you can see some kind of light texturing maybe across the thing, but it's not a driver in any performance.
Okay, then like kind of a piggyback question. You mentioned you guys are doing a lot of like kind of different materials testing. I didn't see any creep. It looked like you were kind of comparing very large grains to very small grains that you guys tend to make. Do you guys have comparable creep data as well, or do you don't really make parts that you worry about creep too much?
We don't have any creep data. I believe some of our users do, but they keep that pretty close to the vest.
Okay.
We have some fatigue data. That's about the most dynamic load we have.
Got it. Okay. And then one more, sorry. So you mentioned there's plastic deformation that's occurring. Can you guys actually like fine tune the dislocation densities based on how much force you're applying, or is that kind of, you don't really worry about that too much?
Yes.
That's cool.
Yeah.